This is section 4.4, and it's on quadratic models and applications, real-world applications that use quadratic models and quadratic functions. So if you look at the top of your notes, it says applications with quadratic equations. And the first one is a very common one. It's called maximizing revenue, obviously one that businesses use. And it says that in economics, the law of demand states that P, which is the unit selling price of an item, and X, which is the number of items that you sell, are related, so that as one increases, the other decreases. Now think about that for a second. So as the price, let's use a calculator as an example, as the price of a calculator goes up, the number sold goes down. But as the number sold, or as the price of the calculator goes down, the number sold goes up. So as one increases, the other decreases. And the equation that relates P and X is called the demand equation. So let's look at example 1. It says the marketing department at Texas Instruments has found that when certain calculators are sold at a price of P dollars per unit, the number X of calculators sold is given by the demand equation. X equals 21,000 minus 150p. So you're given this equation that shows this relationship. So let's look at A. It says express the revenue R as a function of the price P. Well, we know that R equals the revenue, how much Texas Instruments is going to make, equals the number of calculators sold times the selling price. Okay? But we also know that X is equal to this equation that we were given, 21,000 minus 150p. So we could say that R is equal to P, that's this P right here, times our X, which is 21,000 minus 150p. Don't let this get you messed up. This is just common sense. If you go ahead and distribute that, what you're going to get is that R equals, I'm going to go ahead and distribute this and then rearrange, negative 150p squared plus 21,000p, or we could say R of P is equal to that. Okay? Let's look at B. What unit price should be used to maximize revenue? Well, let's go back and look at this equation. This is a quadratic equation, as indicated by the square term there. We know that because our squared term has a negative coefficient, that this opens downward. So it opens like this, the parabola, and this right here is our max point, and it's the vertex. Okay, we also know that A is negative 150, B is 21,000, and C is 0. So when we get to part B and it says what unit price should be used to maximize revenue, we know that the max is equal to the vertex. And we know that the vertex is equal to negative B over 2A, comma, F of negative B over 2A. So we can say that our max, or our vertex, is equal to, just go back to our A, B, and C, and we have negative 21,000 over 2 times negative 150, and then F of that. Okay, F of that. So let's go ahead and on the side here, let's figure out what that is. So that's negative 21,000 over negative 300, which is equal to 70. So what we want to know is what is F of 70. So we'll now figure out F of 70. F of 70, if I go up here, in our equation that we were given of R of P is equal to negative 150p squared plus 21,000p, we have F of 70 is equal to negative 150 70 squared plus 21,000 times 70. Just pop that into the calculator and you will see that F of 70 is 735 thousand, and that's dollars. So the vertex is the point 735,000. That's our vertex point. Okay? So, it says, if this price is charged, what's the maximum revenue? Well, we already figured that because in Part B, we actually went further. I went further than I was supposed to go. So I took you a little bit further. This is all you needed in Part B, is that you would charge $70. Sorry about that. I went too far. All right, D, it says, how many units are sold at this price? Well, let's think about this. At the very beginning of the problem, it said X, the number of units sold, is equal to 21,000 minus 150p. So we're going to say X is equal to 21,000 minus 150. What was the price that maximizes our revenue? The price per calculator that maximizes the revenue is $70. So again, when you put that into the calculator, you're going to get 10,500 calculators sold at the maximum revenue. Okay, this is not a price or an amount of revenue. This is the amount of calculators. And then finally, Part E says to graph R. So what we need to know is that when R is 0, when there's no revenue, that means they're selling no calculators. So those are the x-intercepts. So let's set this up where here is our price. And I think I have it set up on your notes so that I'm counting by 14. So we've got 14, 28, 42, 56, 70, 84, 98. I need to go further. 112, 126, and 140. Okay, that's the price per calculator, and that's in dollars. And then over here, what we have is we have the revenue, the total revenue. And that is in thousands of dollars. Let's do it that way. And since we know the maximum revenue was 735,000, I'm going to go, let's see, 1, 2, 3, 4, 5, 6. I didn't do this enough. So 100,000, 2, 3, 4, 5, 6, 7, 8. This is 800,000. This is 1, 2, 3, 400,000. So pardon my sloppy graphing. Yours will look much, much better. So we want to know what those x-intercepts are. Meaning the x-intercepts, when the price of the calculator is 0, the revenue will be 0. So we want to know is, when is negative 150p squared plus 21,000p, when is that 0? Remember, that's our formula for R. So I can factor out a negative 150p, and I am left with p minus 140 equals 0. And now I have two factors that are equal to 0, so that I know either negative 150p equals 0 or p minus 140 equals 0. So on this one, I just divide by negative 150, and I get p is 0. Obviously, when the price is 0, none will be sold, right? And well, actually they'd be given away, and there'd be no revenue. And we also know, if I finish this one, that p equals 140. So I know that my two intercepts are right here. We also, from when we found the vertex, we know that the vertex is at 70, so it went 14, 28, 42, 56, here's 70. And the maximum revenue there is about here. And if you put that function into your graph, you're going to see something like this. You can graph that in your graphing calculator. But it's really important on these kind of problems that you understand what these applications actually mean. All right, let's look at at the second instance, a real-world application where we use quadratic functions, and that's maximizing area. So example 2 says a farmer has 2,000 yards of fence to enclose a rectangular field. So I'm going to go ahead and draw my rectangular field. What are the dimensions of the rectangle that encloses the most area? So he could make his field in many different rectangles using that perimeter of 2,000 yards, but he wants to maximize the area. So here's what we know. Perimeter is equal to 2L plus 2W. And we also know that the perimeter is 2,000. So, if I label this side as width, I need to be able to name my length in terms of width. And I can do that if I solve this equation with P being 2,000, if I solve that for L. So let's rewrite that as 2,000 equals 2L plus 2W. I'm going to subtract 2W, and I get 2,000 minus 2W equals 2L. Divide each piece, each side, both sides, by 2, and I get L equals, I have to divide that 2 both directions, 1,000 minus W. So this is 1,000 minus W, and I now have my dimensions. Okay? We also know that with a rectangle, area is length times width. So I know the area is, substitute back what I just found for L, 1,000 minus W times width, which is just W. Distribute that out, and the area is 1,000 W minus W squared. All right, so what do we know? Another way to say that, let's rewrite it as quadratic in the correct order. Negative W squared plus 1,000 W. So what does that tell us? It tells us that this is a parabola, a quadratic function. It opens down, and I know that because the A, the coefficient on the W squared is a negative 1. Okay, so I have A is negative 1, B is 1,000, and C is 0. So it opens like this. That's supposed to be curved. This is the vertex. It's also the maximum area spot. It's where the area maximizes as you change the dimensions of your rectangle. So what we want to do, again, is use that formula for the vertex, which we know is negative B over 2A, and then f of negative b over 2a. So we need to find out that vertex. So it's going to be negative b over 2a. And let's do this quickly. That's negative 1,000 over 2, negative 2, which is 500. Okay, so then we need f of 500 as the second piece. Well, to find f of 500, I have an equation. I have an equation right here that I can find out. So a of w is equal to negative w squared plus 1,000 w. So f of, or a of, 500 is equal to negative 500 squared, watch your parentheses, plus 1,000 times 500. Pop that in your calculator, and you get f of, or a of, let's change that to an a because that's what it is. A of 500 is equal to 250,000. Now what do those numbers mean? What do those numbers mean? It means that when the width, a of w, when the width is 500, the area is 250,000. So what I have, and I'm just going to sketch this, I'm not going to actually fill in a bunch of numbers. If I plot W against A, there is a point where my width is 500, width is 0, okay? There's a point where my area is maximized here at 250,000. So it climbs up that area, and then as the width goes back down, it looks like this, okay? Here the width is 1,000. How did I know that? Because remember the length formula, length equals 1,000 minus W? The smallest thing the length could be is 0, and that would be when the width was 1,000. Now, what I want to know is, though, I know that this point is the point 500 width and 250,000 area, but when the width is 500, what is the length? Well, we know that the length is 1,000 minus the width. We said that right here. So the length is 1,000 minus 500, or the length is 500. So when is the area maximized? This is an important concept. When the width is 500 and the length is 500. What kind of shape is that? It maximizes area with a square. A square is the most efficient rectangle when it comes to maximizing area. And that's what we were looking for. All right? Okay, let's look at the next one. Example 3. This is the one about a projectile, the motion of a projectile, which you've been doing since beginning algebra. A projectile is fired from a cliff 500 feet above the water at an inclination of 45 degrees to the horizontal with a muzzle velocity of 400 feet per second. In physics, it is established that the height, h, of the projectile above the water is given with this formula. H of x is equal to negative 32 x squared over 400 squared plus x plus 500, where x is the horizontal distance of the projectile from the base of the cliff. Okay, now you got to think about that. The horizontal distance from the base of the cliff. So it says A, find the maximum height of the projectile. Before we can find our maximum height, you've got to recognize what it is that you are looking at. So we're going to fill in h of x equals, if you do this multiplication, negative 32 divided by 400 squared, you're going to get negative 1 over 5,000, just pop that in the calculator, times x squared, and then plus x plus 500. So now it looks more like a quadratic equation. Our A is right here. It's negative 1 over 5,000. Our B is 1. That's that 1x. And our C is 500. So since it asked for the maximum height of the projectile, we know we're looking for the vertex. So what we're going to say is that the max, which is the vertex, is equal to negative b, negative 1, over 2a, 2 times negative 1 over 5,000, okay? And then f of all of that. So let's go ahead and figure out what this is first, so we know what f we're finding. So it's negative 1 over 2,500. And when you put that into a calculator, what you're going to get is 1 over 2,500. If you pop that into the calculator, and what that gives you is 2,500 feet. So what we want to know is, what is f of 2,500 as our vertex? Okay, we know the first part of that point is 2,500 because I solved that, simplified that. Now we want to know f of 2,500. How do we find f of 2,500? F of 2,500 goes back into our formula, and really we should call it h of, but it's the same thing. So it's going to be negative 1 over 5,000 times x, which is now 2,500 squared, plus x, which is 2,500, plus 500. Put that in your calculator, and I'm going to go back to h. h of 2,500 is equal to 1,750. So that point is the point 2,500, 1,750. So when it says what is the maximum height of the projectile, the maximum height, if we graph horizontal distance against height, the maximum height here is 2,500. And I just said that incorrectly. The maximum height is reached when it's 2,500 feet from the horizontal, along the horizontal, but the maximum height is 1,750, which is exactly what we just figured right here. Okay, let's look at part B. Part B says, how far from the base of the cliff will the projectile strike the water? That means we want to know, when is h of x 0? Because there's no height, so it strikes the water. So that's the question. When does h of x equal 0? So we would say, when does 1 over 5,000 x squared plus x plus 500 equal 0? And this is when you'd be very glad you have a calculator. So let's go back again. Our A is negative 1 over 5,000. Our B is 1. Our C is 500. And we need to put that into the quadratic formula. So it's negative B plus or minus the square root of B squared minus 4 times A times C all over 2 times A, which will be negative 1 over 2,500, or negative 2 over 5,000. Now be very, very careful how you put this in your calculator. That will be approximately equal to negative 1 plus or minus the square root of 1.4 all over negative 0.0004. All right, and when you do this as negative 1 plus square root of 1.4 all over negative 0.0004, and then you do it as negative 1 minus square root of 1.4 all over negative 0.0004, you get two answers. You get negative 458, and you get 5,458. Well, a distance, because it's asking you how far from the cliff, so that's a distance, can't be negative. So we know that this is our solution. At 5,458 feet from the base of the cliff, it hits the water. The height is 0 again. So make sure when it's plus or minus, you put in both so that you can see what it is that you get. All right, finally, let's do example 4. This is finding an equation of best fit. It says a farmer collected the data in the table to the right, which shows crop yields Y for various amounts X of fertilizer used. So you see the plot number, how much fertilizer was used, and then the yield. It says A, draw a scatter diagram of the data. Comment on the type of relation that may exist between the two variables. Now, this is what you need to do. All right, let's go back to A. I'm sorry for the interruption. I don't know where I was. We're going to have to start over again. It says draw a scatter diagram. Okay, that's just plotting your X and Y's and putting those into L1 and L2. Make sure you use L1 and L2 in your calculator, because when we do the regression, it's going to automatically use L1 and L2. So if you don't use L1 and L2, you'd have to tell it something different. So just do that. So the fertilizer used is X, and the yield is dependent on how much fertilizer is used, and that is your Y. And when you enter that into stat edit as L1 and L2, and you see the scatter diagram by hitting, you can just hit graph and then do zoom 9 for zoom stat. Now we're ready to actually look at that scatter plot, and mine isn't going to be accurate, but it looks something like this. There's kind of a double thing that goes along like this. So it makes us think that yes, it probably is quadratic. Okay, so now it says use a graphing calculator in B to find the quadratic function of best fit to these data. So we want to know what is y of x. So these are the steps to do the quadratic regression. You're going to hit stat and then hit your right arrow over to calc, and then number 5, which says quadratic regression. Now, because we know that we're using L1 and L2, then you can just go ahead and hit enter. You don't have to tell it a different list. It's going to automatically use L1 and L2. And what you're going to see when you pull that up is it's going to say y equals, it won't have of x, y equals ax squared plus bx plus c, and then it's going to tell you that a is negative 0.171212121, I think that's what it shows, and b is 1.0765. I'm not going to write this all out, okay? It continues. And c is 3.893939394 or something like that, okay? Now, it says use that to find the quadratic function of best fit to these data. So what you're going to do is put this A here, the B here, and the C here, and you're going to get y of x is equal to, and I'm going to round these off, negative 0.0171x squared plus 1.0765x, I'm rounding off, plus 3.8939, okay? Excuse me. Part C says, use the function found in Part B to determine the optimal amount of fertilizer to apply. That's right here. That's that vertex. That's the max point. Okay, so that's our application again. It's the optimum amount of fertilizer. This is X, the fertilizer, to give us Y, our yield. And if we want the most yield, we have to know what is the amount of fertilizer that we need right here. So what we need is to find negative B over 2A. We already have our A, our B, our C. So we have negative 1.0765 over 2 times negative 0.0171, and that's approximately 31.5 pounds of fertilizer. So on this point right here, the first coordinate is 31.5, and then in Part D it says predict crop yield when the optimal amount is applied. In other words, when you use this amount, how much is the yield? So what is Y of 31.5? Which is simple enough, because we're going to put back in our original equation the 31.5 plus 1.0765 times 31.5 plus 3.8939. Put that in the calculator and you get about 20.8 bushels, I believe is the way, if you look back at the chart, that it's labeled. You could also find this out by using your table function. So if you went back to second table and you went down and you looked at your list 1 and list 2, you would be able to see where it maxed, where the maximum number of bushels was, and at what X value that was. Alright, for homework, to practice these kind of problems, you need to do problems 3 through 29 every other odd. When you do these, you're going to realize basically they all work the same. The words are just different.